As you said, my name is Francesco Petruccione. I'm the director of NITheCS and also a professor of quantum computing at Stellenbosch University. Yeah? What I want to speak to you, and I will try to keep it short because I know that we are running late, and we don't want people to delay too much. Yeah. I would like to show you how we can automate the design of machine learning algorithm, yeah, using some inspiration from theoretical many-body physics. Basically, the idea is to try to have to do the machine better than the human in designing the architecture for the algorithms that we want to implement. Yeah? I will start with some background and motivation. I will then show how it works and end with some applications. Yeah? Oops. Voilà, here. So let's start with the background and the motivation. Yeah. The motivation is essentially inspired by what happened in the classical machine learning world. Yeah. So until more or less 2012. Yeah. And this is just a standard textbook of the time. Yeah. All the machine learning models for pattern recognition and other applications were essentially done by hand, in the sense that the fields that were designed by expert, yeah, based on knowledge, essentially, yeah. After 2012, yeah, that's where really the deep learning revolution started, yeah, and this is one of the papers that put all of that in motion. Yeah, is that the qualitative shift was to learn features automatically. Yeah, so the deep learning network was able to do automatically what the previous era machine learning algorithm could only do essentially by hand. Yeah. And this led essentially to what we call now the neural architecture search problem. Yeah, just to optimize the architecture of the network so that the features are recognized and learned more efficiently. Yeah. So the basic idea is the following. Yeah. As I said, to automate the design of the deep learning architecture, yeah, you start defining a search space. You need a search strategy. You start with some architecture, you estimate its performance, you optimize some parameters, yeah, and you go back until in this loop until it more or less converges and does what you expect it to do. Yeah. So essentially, if on the left-hand side you see some schematics of different architectures, yeah, each graph is sort of each node is a layer in some neural network, and you can have various and you have canonically fixed architectures. Yeah, usually you start with one structure like this, and you keep going. Yeah. The idea now is that you can develop other approaches, yeah, and I will explain in a minute why this approach is hierarchical, yeah, because we want it to adapt automatically within the context of variational approaches. Yeah. So the idea is the following: yeah, you define kind of basic building blocks of your network, yeah, like illustrated in the line on the left hand side. Yeah, you can have, for instance, if you look at the three pink dots, that's a typical pooling kind of element, yeah, of a convolutional neural network. Yeah, and you can assemble these to build bigger structures. Yeah. So the idea is essentially to define this elementary building block, and then let the algorithm learn hierarchical how to put them together for a certain problem. Yeah. So this is the classical strategy, and the idea of what I'm going to tell you now is that you can apply it essentially also to quantum computing algorithm, yeah, with great impact. Yeah. So the idea is now the following. Yeah, I mentioned earlier that the inspiration is from traditional quantum many-body physics. Yeah? And one typical tool that is used there, a tensor network. Yeah? A tensor network essentially is an object with legs, yeah, if you want. Yeah, and you can have a like in under A, a very general one where you have many legs and many connections in between them. Yeah. But for our purposes, it is useful to have a better structured tensor network. Yeah, for instance, under B, you see a very kind of linear structure of nodes with legs all going in one direction. This is what we call the matrix product state. You can have then also more complicated, they're called PEPs, projected entangled pair states, like in C, or three tensor networks like in D, or really multi-scale normalized entanglement Ansatz like in E, yeah, which is a little bit more complicated, but still very nicely structured. Yeah. So this is the basic technology that we are going to use. Yeah. Our aim was to apply to quantum machine learning. And in line with my first slide, convolutional neural network, the game, yeah. And in the top figure, you see the structure of a typical convolutional neural network, yeah, with convolutional layers and pooling layers and so on and so forth, yeah. And this can be mapped essentially one-on-one to a quantum convolutional neural network using one of these tensor network structures that I mentioned before, yeah, and typically this Mera one, yeah. And what is interesting is that the Mera approach and the quantum convolutional neural network really map each other in opposite direction, yeah, if you want to say it like that. Yeah, so the starting point, as I mentioned, is to identify the elementary building blocks. Yeah, we are sometimes also called the primitive. Yeah, and here in the case of a network with 8 nodes, with step 1, we can represent it in this way, graphically, yeah, on the left, and as a quantum circuit on the right. Yeah, another possible building block, this one with step 2, yeah, represented graphically on the left, and in a quantum circuit way on the right hand side. Yeah. The basic idea is, of course, to combine the two. Yeah. So once you have the building blocks, you can combine them in many ways. Yeah. So you can combine in many ways, but you want to find the optimal combination of the primitive building blocks for your purposes. Yes, and here is where evolutionary strategy come into place. Yeah, so this is a little bit of a busy slide, but it shows all the steps that the algorithms that we developed have to follow. Yeah, for instance, you start with the identification of the primitives. In this case, it's just pivots and cycles. You compose them in B. You need to initialize your quantum computing circuit. Then you start the evolutionary search. If there are symmetries in the system, that's always a good idea to keep them. Yeah, so if the search breaks them, you fix them, and so on and so forth. Yeah, and by iterating this approach, you hope to get a very efficient, condensed, small system. Yeah, and this is a paper that will be published next week in Physical Review Letters. So let me show you some applications of all of this. Yeah, a typical problem that quantum computers are supposed to be good at, yeah, is to find the ground state of various models. Yeah, for instance, here I will show you. I will use two systems. Yeah, a Lipkin-Meshkov Glick Hamiltonian. Yeah, and a typical Ising Hamiltonian at the bottom in two. Yeah. So let's see how we generate the ansatz for the two models. Yeah. By coincidence or not coincidence, the same ansatz, more or less same ansatz, is generated for both approaches, and very interestingly, yeah, this turned out to have also implication on not only on computational methods but also on analytical methods, because it turned out that, and this is really a fantastic result, that with this approach, you can develop a systematic way to go beyond mean field theory. Yeah, and this came out of our algorithm in a very beautiful way. Yeah, and it's a sort of just let's ignore maybe the equations become probably too technical, but in the quantum circuit, you see that there is one component on the left that can really identify it with a mean field theory, and a systematic approach to go beyond midfield theory. And for instance, if you look at the magnetization of the LMG model and compare it with the exact results, you really see that the simulation is really essentially perfect. Yeah, even for large numbers of n, you follow very nicely the mean field theory exact prediction. Yeah, so this is really very encouraging. Yeah. Also, if you look at the relative energy errors, you see again a very nice behavior. Yeah. Same for the Ising model that has a long range correlation, which makes it particularly challenging. Yeah. And here we see that our ansatz strongly improves on the mean field theory. Yeah, you see the dotted line is a mean field theory, but it's still not exactly exact because it's sort of some kind of approximation. Yeah, but for not too large n's, the prediction that the model of the ansatz are really very good. Yeah. One can really show, yeah, that that the ansatz is really robust. Yeah, if you do it in different setups, the search consistently rediscovers the same ansatz. Yeah, so it's not an approach that sometimes leads to success and sometimes not. It's really a solid, robust approach. Yeah. Another very interesting and technically challenging problem is the recognition of quantum phase transitions. And to demonstrate that the approach is valid also in this case, we used a very simple, relatively simple cluster Ising Hamiltonian as illustrated here. Yeah. And the question that one wants to address is if someone gives you an unknown ground state, in which phase will your system be? Yeah, and and here we compared our approach with previously published results for the same system. Yeah, and on the left, and you see that our approach leads to a much better definition of the phase transitions in the model. Yeah, which was very rewarding. Yeah. Yeah. What is really close to sensational, yeah, if you compare, like we did here on the left with the previous quantum convolutional network approach to the same problem with ours, you see, if you look here on the table on the right and the metric, yeah, the original approach had 1,308 parameters, yeah, to recognize the phase transition. In our approach, we have only 11. Yeah, so that it really reduces dramatically the number of gates and parameters that you need to run the simulation, yeah, to run the algorithm. Yeah, so this is a really very important achievement, I think. It gets even more interesting, yeah, because What we've also were able to show, and this was part of the PhD thesis of Amy Ruyard, is to see if one can use this same evolutionary based approach to discover quantum algorithm. Yeah. So, and we were able to show, for instance, that you can automatically, even if you don't know about it, yeah, you can rediscover, for instance, the Deutsch algorithm, yeah, that comes out automatically. Yeah. In a similar way, if you train your system to search, our hierarchical approach reinvents the Grover algorithm. Yeah, so it's a really very efficient tool. Yeah, and it can also reinvent quantum Fourier transforms and so on and so forth. What we were not yet able to do is to invent an algorithm that nobody else has invented before us. Yeah, but we are pretty hopeful that we will get there pretty soon. Yeah. Well, our very first motivation for all of this, was essentially in time series analysis. Yeah, we wanted to see if with this improved version of convolutional neural networks, the quantum version thereof, we can classify music genres. Yeah? So that was our first original motivation. I didn't follow here in my presentation the historical trajectory. I used a bit of another approach. Yeah? And and it turned out that that our approach is really very accurate. Yeah, the accuracy compared to standard other quantum machine learning approaches to music classification is really much better. Yeah? For instance, here we were trying to distinguish between rock and country music and things like that, and it was a substantial improvement, yeah, bringing it from the, let's say, from the 60% level to the almost 80% level, which was very good. Yeah. Yeah, coming to an end, I rushed a little bit, but I was trying to help the organizer to get back in the control of the time. Yeah, I just showed you, yeah, that it's really possible to automate the design of variational approaches to quantum machine learning using standard tools from quantum many-body physics. Yeah? And the strategy is always to start identifying primitive elements, combine them, apply evolutionary searches, and find the optimal results. And I think that the examples that I showed you demonstrate clearly that we were on the right track, and that this approach really works nicely, and we are hoping to find many more useful applications and to improve it even further. As I mentioned before, this was mainly part of the PhD thesis of two students, Matt Lawrence and Amy Ruyard. Yeah. So thank you very much.